Hey guys, welcome to the second part of lecture 4, week 4, whatever, or 5. We continued, this is the second part from the Combinatorics lecture. I didn't have time to do too many problems using the Pigeonhole Principle, so I would like to continue doing so, and maybe if time will allow, and I hope it will, I will talk a bit about graph theory. You know, there are so many things to cover in combinatorics, and I cannot cover everything. Unfortunately, I have to leave out things like invariance, like generating functions, and some other topics, Ramsey theory, and some other topics as well. So I would like to dwell more on topics that are more likely to appear on the Putnam, such as Pigeonhole Principle or maybe some graph theory, although I haven't seen a graph theory problem recently, but I think it's a good topic to cover. Well, unfortunately, as you can see in my background, this is not Bahamas or Hawaii, although I'm dressed like I'm on the beach right now, but actually I'm in my office. Yeah, that's so sad. Anyway, I think we can get started now. I would like to continue with, just like I said, with the Pigeonhole Principle. All right. And let me do the following problem. And last time, if I remember correctly, we've done a problem. Remember that problem with the triangle, equilateral triangle with side length 1. And I have 5 points inside, and we have to show that there exists at least 2 points with distance less than 1/2. Anyway, now let's consider again 5 points, but this time the problem will be a bit different. So we'll consider, I'll emphasize a bit on this problem because it will be important when we will solve another problem. Consider in the Euclidean plane. This is a very classical problem, plane, 5 points. And in fact, you will see that in the recitation, one of the problems that will be solved in the recitation will be very similar to this one. It will be the 3-dimensional analog of this problem. Anyway, considering the Euclidean plane 5 points of integral coordinates, so these are lattice points. Okay, show that there exists a point of integral coordinates which is, in fact, I'm just going to say it, maybe I shouldn't, but which is the midpoint of the line segment determined by 2 of the 5 points. All right, so that's the statement. Well, it's pretty clear what you have to do. Well, now we have 5 points. So our intention is to apply the Pigeonhole Principle, but how we should apply the Pigeonhole Principle? So every point is a lattice point, right? So keep in mind this. So every point has integral coordinates. Right? And since it's in the Euclidean plane, we'll have, each point will have 2 coordinates. Let me say here this is a lattice point. So every point has integral coordinates, and we can, the main trick here is to separate these points into 4 classes. So we have 4 classes of points. And that's very important. And we'll separate these points. So we'll put them in each class based on their coordinates. So we will have the following. The first class, let's call the C1, will consist of those points which will have coordinates odd. So we'll do this based on their parity. So since they're integers, why not do it? The second class, C2, let's say they have odd even. The third one will be even odd. And the last one, C4, will be even. You see, I have 4 classes of points. I have 5 points. So since, let's write it, since there are 5 points, by the pigeonhole principle, it follows that there at least 2 points, let's put it this way, at least 2 points fall into the same class. Right? So at least 2 points out of those 5 will have both of them either odd coordinates, or odd even odd, and even. So 2 of them will be on this category. And now clearly the midpoint of the line segment determined by these 2 points is a lattice point. And let me explain a bit, why is that clear, lattice point? Why is this clear? Well, if you have 2 points, let's say A, of coordinates x1 and y1, and keep in mind x1 and y1, and let's say we have B here of coordinates x2, y2, then the midpoint, keep in mind from analytic geometry, from Calc 1, the midpoint M will have the coordinates x1 plus y1 over 2 and x2 plus y2 over 2. So anyway, so imagine that these x1 and y1, suppose they're both odd, right? They're in the same category. So if you add odd plus odd, it will give you even, divided by 2 will be even. So it will be in integer, right? You can divide by 2. So anyway you do it, it's the same thing. And that's it. So that's the proof of it. Keep in mind this problem, this idea, because we will use it, you'll see later on. All right, now let me do another problem. Let me veer towards another problem, another geometry problem. So problem 3, and this problem 3, I would say this was a Putnam B2, no, sorry, A2 in 2002. And the problem says the following. Again, it's not a hard problem, but anyway, let's write it. Show that given any 5 points, again, 5 points, I think I have something with, and anyway, it wasn't intentional, it just happened, on the surface of a sphere, of the surface of a sphere, there exists a closed hemisphere which contains at least 4 of the points. Wow. So out of those 5 points, there will be a closed hemisphere. So any way you pick 5 points on a surface of a sphere, you can find a closed hemisphere which contains at least 4 of them. Wow. Well, in fact, it's quite good. Let's look at it. So I have 5 points on the surface of a sphere. That's important. So I want to show that there exist at least 4 of them. So maybe, so I have 5 points. Maybe I should divide. There's a trick here. And maybe, let me just draw a picture. So I have the sphere. So let me do it like this. Let's just say this is a sphere. Well, it doesn't quite look like one, but let's just say that's right here, sphere, just in case. All right, so we have this sphere, and suppose we have 5 points somewhere. In fact, you know what? I'm going to pick 2 points here, but anyway, it doesn't really matter. Let's say I have another. You see, anywhere I draw, it will be at least 4 of them in one hemisphere. Well, I tricked you here. So what I'm going to do is to divide the sphere into 2 hemispheres by choosing a great circle that passes through any of these 2 points, just like I did here, right? So I divided this into 2 hemispheres. Look at them, right? This one here. Just, they're actually, and this one here. But anyway, you can divide it any way you want along a great circle. You can take these 2 points. Oh, sorry. You can take other 2 points, so it's not all right. So these are the 2 hemispheres, right? Okay. Well, as you can see, 4 of them, 2 of them are already contained because I divided by I divided by a great circle that passes through any 2 points. And now it's quite clear by the pigeonhole principle. I have 2 hemispheres. I have 3 points left. So 2 hemispheres, 3 points left. So at least 2 of them will fall into one of them, on one of the hemispheres. So, and you already have 2, so there will be 4. All right, let's write this down. So that's basically the idea of the problem. That was the trick. So let's write it down. Okay, let's see. So we divide the sphere into 2 hemispheres. All right. And by choosing a great circle passing through any 2 points. All right, that's a great. I can do this. So by the pigeonhole principle, it follows that that at least 2 of the remaining 3 points, of the 3 remaining points, let's say, must lie in one of the hemispheres. And there you go. Now you have 2 points, then you have other 2 points, then you have 4 points in total. but then we have 4 points in total. And that's it. And we're done. You see, let me say that this is H1. Let's say here's the H1 and this is H2, this second hemisphere. I think the picture says it all. All right. So that was the problem. As you can see, it was an easy one. It was a Putnam A2. All right. Now let's see problem 4. Let me, since in the recitation there will be a, well, I'm not sure if I will cover, but there will be a problem with some numbers which have to be the side length of a acute triangle. Let me do something similar. This is a classical problem. It's very nice. I think you should know this. Let's consider, let us consider 2n plus 1 real numbers, right? So we'll consider 2n plus 1 real numbers that are greater than 1 and less than 2 to the power n, let's say. Show that there are 3 of them such that they are the side lengths of a triangle. Okay, we have this. All right, so again, this is a problem. I have 2n plus 1 points, so I have to come up with 3 of them such that they are the side lengths of a triangle. So we should be careful here. And we have to look that these numbers, keep in mind that these numbers are in this interval. It's between 1 and 2 to the n. So maybe I should divide this interval. So we consider the partition, let's say, of the interval um, 1, 2 to the n into n subintervals so that's the partition we'll consider. And now let's see, 1, 2, then 2 squared, then 2 squared, 2 cubed, and we keep going. The last one will be 2 to the n minus 1 and 2 to the n. Well, how many of them are there? Let's say here is 2 to the 0 and here is 2 to the 1. So you see there are n sub-intervals, right? And I have 2n plus 1 numbers. So these are n sub-intervals. And now, since I have 2n plus 1 numbers in n sub-intervals, by the Pigeonhole Principle, there exist three of them three of these numbers such that let's say okay, let me call these numbers let's say 3 of them, let's say A, B, C, such that So that A, B, C, so these numbers are in this interval. Let's say 2k and 2k plus 1. For k from 0 to n, right? So they're in this interval. Well, it's quite clear now that these will be the side lengths of a triangle because the sum of any two is greater than the third one. So clearly now, when you add them, a plus b will always be greater or equal than, well, 2 to the k plus 2 to the k, but this is 2 to the k plus 1, which is strictly greater than c. So there you go. That's it. All right, so this was an easy problem as well. Now let's do a harder one. So we'll do 2 harder problems now. So problem 5 will be a Putnam. This is a Putnam A4 in 1993. Well, it's actually, you need to understand the statement quite well. And the statement says the following: let us consider, let x1, x2, x19, so we'll consider a set of 19 positive integers, be positive integers. And they have the property each of which is less or equal to 93. All right. And now I'll consider another set of positive integers, but this time I will consider 93 of them. So let us consider, let y1, y2, y93 be positive integers each of which is less than or equal to 19. Prove that, well, actually, this is very artificial. You will see why. Prove that there exists a how was it? Prove that there exists a non-empty sum of some xi's equal to a sum of some yj's, of some yj's. Okay, so that's the problem. Look at the statement. Anyway, what I'm trying to say is that it doesn't really matter if it's 19 or 93. It's, like I said, it's very artificial. Yeah, I think that's... So for the sake of generality, we'll replace those numbers, 19 and 93. We don't want to deal with that. So we replace the numbers 19 and 93 with M and N. I think it's much more convenient to do so, right? And now we define, let me take the sum of these. So we'll define these numbers, let's say capital XK as the sum from I, which goes from 1 to K of these numbers XI's, right? So this is capital XK. And we also define in the same fashion, let's say capital YL as the sum from j, from 1 to L of yj. All right. We want to show that at some point these two sums are equal. Anyway, that's what we want to show. Now, without loss of generality, we assume that, let's say, xm is greater or equal than yn. Okay. So we assume this. And now for L between 1 and n, we define this thing. So we define f of L, and in the following way, I'll define this index, f of L, by the following. And now this will be a crucial condition because it will help me by the following. X of f of L is less or equal than y of L, and this will be strictly less than x of f of L plus 1. Right? So by this I will define. And now, guess what happens? Well, because of this condition, it will follow that. So it follows that f of L is between 0 and m. So 0 is less than f of L, and it's less than m. Well, that's obvious. And now what I'm going to do is the following. I will define, I will consider now, so consider g of L as let me see. So we'll consider g of L as, okay, y of L minus x of f of L, right? Now, we want to have a discussion if g of L is 0. So if these two are coincide. So if g of L is 0, right, for some L, we're done. The problem is over. We're done. Otherwise, g of L will be, so let's write it as y of L minus x of f of L. This is L here, not E. The f of L, right? And this is less than, based on our inequality there, is less than x of f of L plus 1. And this guy is less than n, right? We apply the above inequality because this is the way we define. All right. Okay. All right. So from here, this will imply, so we'll have a similar inequality for g of L. So this will imply that g of L, this index, will be between 0 and n minus 1. So keep in mind we have these two here. So this guy is, and this guy is like this. Okay. Well, then this happens whenever, well, whenever L is between 1 and n, right? Okay, now if you look at it, now we're ready. If you see, I'm ready to apply the pigeonhole principle, right? Because I have less, so g of L is between 0 and n minus 1. So this implies that I'll have two indices, let's say L0 and L1. So by the pigeonhole principle, it follows that there exists L0 and L1, let's say L0 less than L1, such that G of L0 is the same as G of L1. Well, but that at this point is obvious when I add them, but then we have that the sum, okay, I'm going to write it here. And when we sum up from f of L0 plus 1 to f of L1, so we're going to sum up from here. So then we have that the sum from f of L0 plus 1 all the way to f of L1 of xi, this will be nothing else than just based on how we denoted this above here, right? This will be x of f of L1 minus x sub f of L0, but this is nothing else than just y of L1 minus y of L0, and this is, again, I can write this as the sum, and this time we'll have yj's, and this j will go the same from L0, this time we'll go from L0 plus 1 all the way to L1. And that's it, we're done. You see, Pigeonhole Principle will guarantee that there exists, oh my God, oops, sorry. There exists L1, L0 and L1 such that this happens. Okay, that's it. It was a tricky problem, I would say. That's very tricky. Yeah. All right, now let's see problem number, this was problem 5, problem 6, and probably this will be the last one with for Pigeonhole Principle. This is a beautiful one. It was a Putnam A3 in 1990, and I'll explain immediately why we will have to use the first problem that we did today, so the second problem of from the Pigeonhole Principle. Well, the problem says the following: prove that any convex pentagon whose vertices, again, are lattice points, vertices, and I would like to say I would like to emphasize that this is important, not 3 which are collinear, so they're on the same line, have integer coordinates, so they're lattice points, must have the area, greater or equal than 5/2. So that's the problem. So this is the Putnam problem, A3 from 1990. It's a very beautiful problem, I would say. And I would like to, it relies on 2 facts, basically. I think we've done this in one of the recitations when we talked about geometric inequalities. Remember, I told you about the Pick's theorem, Pick's theorem, how to compute the area of a polygon that if the vertices have are lattice points. And we deduced that the area of a triangle, of a lattice triangle, the area is at least 1/2. Remember, there was a problem, a Putnam problem, actually, if I ping from A3 from 71. If you go back to the geometry lectures, you will see it there, and which said exactly this, that the area of a lattice triangle is at least 1/2. So we'd like to use that in this problem. And not just that, we will also use the idea from the first problem that, remember, I have a convex pentagon, so I have 5 points. And these 5 points have integer coordinates. So remember, we can divide these 5 points into 4 categories. Anyway, we'll like to use that. But before that, let me just gives this problem a little bit of generality, so we don't want to lose too much time with cases that don't matter. So without loss of generality, I can assume, so let us consider the lattice pentagon. Let's say A, B, C, D, E, right? There are 5 of them, of minimal area. So we like to do that. Well, since the area always exists, so let me explain here. The well, since the area always is always, okay, let me put it this way, is always half an integer. Keep in mind, by Pick's theorem, right? The minimum always exists. So I'll assume this. And now let me consider something. So because let me make the following observation, because this will be very important in the problem. So I have this pentagon, right? So now let's see if the interior, well, if the interior of how should I say it, of let's say of side AB contains a point F, right? Because this observation will turn out to be crucial for our problem. So if the interior side, let's say AB, contains a point F, then, well, guess what? I will consider then this pentagon AFCDE, right, is a convex lattice pentagon of smaller area, of smaller, okay, of smaller area of well, okay, of the small area which contradicts the choice of our pentagon, because we consider the pentagon A, B, C, D, E of minimal area. So this will contradict the choice of A, B, C, D, E. All right, that's great. So at this point, we know that there is no way we can have an interior point of any of the side lengths of the pentagon. So now we can apply this argument to each side. So we may assume that the boundary points, so applying the same argument, to each side, to the other sides, to each side, we may assume that all boundary lattice points right, are vertices. That's great. At this point, it's clear what we have to do. So let's draw the picture. Okay, I'm just going to draw it here. A, B, C, D, E. So that's my pentagon. It's a oh, Jesus. It's a convex pentagon. All right. So this is the convex pentagon, A, B, C, D, E. And now, guess what? We will use the idea from the previous problem. So now we'd like to separate. So imagine I have 5 points, and I would like to separate these, and these 5 points are of integer coordinates. So all of them. So keep in mind that A, B, C, D, E, these 5 points are lattice points. This is very important. Well, guess what? We can say now we can use the first problem, right, that we did today, that the first problem discussed in this lecture, and we can separate these vertices into 4 classes according to the parity of their coordinates. So again, using problem, let's see, I think it was problem 2, we can separate these 5 points into 4 classes according to the parity of their coordinates. Remember, we separated, well, I'm not going to write it again, but remember we separated these points in, there are 4 classes with their coordinates odd, 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 even, even, odd, and even, even, right? All right, by the pigeonhole principle. So by the pigeonhole principle, right? It follows that one class, give you my 5 points in 4 classes, one class must contain at least 2 vertices. And now guess what? I'm going to take the midpoint. So now the midpoint, again, basically I'm just applying the problem, the first problem we discussed today. The midpoint of these 2 vertices is a lattice point. And now let's see. Well, keep in mind, so let's look at this. Let's look at it. Keep in mind that, for example, M, let's take the midpoint to be M, cannot be here. We said why, because it will contradict the minimalities, cannot be here. So let's forget about this, right? So M has to be somewhere, let's say, let's put it here, for example. So it has to be at the midpoint. Let's call this midpoint M. Of these 2 vertices is a lattice point. So M, so keep in mind that M must be in the interior of the pentagon. A, B, C, D, E. All right. And now guess what I'm going to do? I'm just gonna draw line segments from A to the vertices. So let's do that. You see, I've already done this, but let's do it. So I'm gonna draw to this. I'm gonna draw to here and also to E. Let's look. How many triangles do I have? Well, let's look at the, I have here this one triangle here. In fact, let me, oops. So I have here, this is the first triangle, T1, as you can see it here. Again, here, this is T2. Again, this is the third one here, T3. This is the fourth one here. Look at it, T4. And now, finally, the fifth one is right here, T5. So I have 5 triangles from that point M, from that midpoint. It's a lattice point. And if you look at these 5 triangles, all of them are lattice triangles. So the triangles T1, T2, T3, T4, and T5 are lattice triangles. In other words, since this is a lattice triangle, we know that the area of any of Ti is greater or equal than 1/2 for I, 1, 2, 3, 4, and 5. So we know that. Now the area of the pentagon A, B, C, D, E is nothing else than the sum of the areas of these triangles from T equals 1 to 5. But the area of each triangle is greater or equal than 1/2. So this is greater than 5 times 1/2, which is 5/2. And that's exactly what we wanted to prove. And that's it. So this finishes off the problem. Well, it's a very beautiful problem. As you can see, we used it for the first problem discussed today, and also we used another problem, Putnam problem, that we discussed in the geometry lecture. That was a really, really beautiful, I would say. Okay. All right. I think I should. I think that's enough with the pigeonhole principle. And I think you have many ideas, and also you will see that in the recitation we will solve even more problems, more Putnam problems using the pigeonhole principle. Well, I think it's more than enough. Now, like I said, I would like to talk in the remaining time, about something. And I don't know, I was debating what topic to choose or whatever, but at this point for me, I think I will choose doing something about graph theory. Anyway, like I said, this is a whole course in combinatorics. I'm not gonna cover everything. I'm just gonna, run through things, basically. That's what I'm gonna do, like, basically just glance through the material. I'm just gonna say, I will emphasize on the most important facts about graph, on graph theory, and maybe do some, maybe I will talk about Euler's formula as well for planar graphs, and maybe we'll see an application of a Putnam problem, because I think in the worksheet that I gave you, there's another Putnam from 2013, I think. Anyway, it was a icosahedron problem, and basically just an application of Euler's formula. So I want to get to that, at least that I want to do. So I'm not gonna go too heavy on graph theory. But anyway, let's get started. Well, I'll start with the definition. A graph, and this I'll denote this graph in the following G. So G stands for the graph, and it will be this pair V and E. Well, this guy here, G, V, and E. V will be okay. Let me say it consists of a set, let's say V, which we'll call this of vertices, right? So this will be the set of vertices. Right? And a set E of edges. All right, so this is a graph, and each of which is a two-element subset of V. So that's basically the definition of the graph. So the way we think about this is in the following way. So I'd like you to think of vertices as points put down on a piece of paper, right? So this is what we'll call the vertices. And the edges are as arcs joining these two, these pair of points. So this is how we should think of it. Anyway, there is no geometry here to a graph, so forget about it. All that matters is which pair of points are joined, not exactly the position of the points. So I hope I make myself clear, or the nature of the arcs joining these points, right? All right. So you'll see that this tool will become very useful when we think of a problem. And the first problem, which is it's a very famous problem that I have in mind, and in fact, is the following: is the party people? I don't want to say party people problem, but anyway, and in fact, is the handshaking lemma. But anyway, let's state it in a more combinatorial way. And it says the following: N people go to a party. Well, it has many equivalent statements, but I'm just going to state it this way. And each one counts up the number of other people a person knows at the party. Okay. Show that there are even okay, there are an even number of people wait, let me see. Show that there are an even number of people who come up with an answer that is an odd number. I hope this makes sense. Let me see. All right. So let me, well, assuming, yeah, knowing here is two ways. So if I know a person knows another person, then the other person knows the first person. So it's like a two-way relation. So I know you if and only if you know me, something like this. All right. I think this makes sense. Let's look at the problem. Let's think of it. How would we approach this? So let's model this. Let's transform this problem into a graph theory problem. Right? Now, how are we going to do it? So now we'll consider let V, so the set of vertices, is the set of the n party goers, let's say. Right, the party people. E, edges, will consist of all pairs of people who know each other. Right? I know you, you know me, so we can, this will be the edge, the edges. And now, let's see. Now, for each person, in fact, for a person, let's say this person I, right? We pick a random person I, right? We denote by di, d sub I, right? The number of edges right, that involve I. Okay, and keep in mind that these I will be, it will be nothing else than just is the degree, is what we will call the degree of vertex I. This is important. Right? Okay. So, okay. Well, we have the following. We have that if we sum up all these degrees, it will be nothing else than, so the sum of all these di's, I'm going to say from 1 to n, right? We have n people will be nothing else than just 2 times the e, right? Since we run over, so we have this formula. Very important. Well, this is clear since we run over all vertices and count degrees. So it follows that each edge gets counted exactly twice, right? So that's the sum of the degree. That's why the sum of the degrees is even. That's exactly what it says, basically. But if there were an odd number of vertices with odd degree, the sum will be odd, right? So there are indeed an even number of people who know an odd number of people. So that's the problem, basically. It's just this formula. And let me point out this remark here, that this useful fact, which says the following. So this basically, at the heart of this problem that I just mentioned lies this fact, that, so for any graph G, we have that, I'm going to write it again, the sum of the degrees is nothing else, it's in times E. All right. Oh, okay. So that's the most classical thing to study for a graph. Now let's see. There are so many things to cover. Maybe I should. Well, another useful fact about graphs is the following, and it's very important. Now that I remember, is that in fact, maybe I should state it as a problem. But anyway, no, let me point out as a fact for in graph theory language, and then I'll state it as a problem. I'll leave it to you to figure it out. Why is this true? So the useful fact is the following: for any graph G, right, there must be two vertices with the same degree. Right. This is, and the way you do this, it's easy. So the problem here is the following. So basically, it says show that two of the people of a party have the same number of friends. Right? That's exactly what it says. Anyway, now, oh my God, there are so many. I have to talk about what is a walk in a graph with adjacency matrix, Hamiltonian cycle. There are so many things to cover. Yeah, so many things to cover. So maybe I will just okay, let me do some definitions. Well, a walk in a graph from, let's say, from a vertex of U to a vertex V, right? Well, not necessarily distinct, right? And let's say that, so, okay, so, how should I say it? Okay. So a walk in a graph of vertex U to vertex V is list, all right? Not list edges with, okay, with U is first, right? Right in the first. okay, and V in the last. Well, that's kind of obvious. And every pair of, and well, sorry about that. Oh. All right, so we were talking about, well, this definition of a walk, right? So a walk in a graph from vertex U to a vertex V is list list of it's a list of edges, right? With U in the first and V in the last, and every pair of consecutive edges sharing a vertex in common. Basically, it's a way to trace a path from U to V, always using complete arcs of drawing and never taking a pencil or paper. Anyway, so, well, I would like to, there's a theorem of Dirac, but anyway, I don't want to talk about it. I would like to say something about a planar graph. You know, there are many definitions here. So also, I can talk about the connected graphs and so on, about trees. But now I would like to say a few things about the planar graph. So another definition, a planar graph right, is a graph that can be drawn in the plane with no two arcs, meeting. So no two arcs meeting except at a vertex. At a vertex. All right. If they have one in common. So let's specify that if they have one in common. So that's what this is what the definition of a planar graph. And now a planar graph, well, let's say, so a planar drawing, because I want to veer towards Euler's formula. So a planar drawing of a graph partitions the plane. So it will partition the plane in the following way, into connected regions. Right? And we call this connected regions called faces. Okay. Well, now we have the following theorem of Euler. He discovered the following remarkable formula theorem. This was due to Euler, among many other things that he discovered. And the theorem says the following: if I have a planar graph, so let G be a planar graph with V vertices, E edges, and F faces. Then we have this following remarkable formula, which says that V minus E plus F equals 2. Well, this can be proven by induction. I'm not going to dwell on the proof of this, and I mean, we don't have time for this. Well, let me just give you some examples of planar graphs, and we would like to see how we apply this formula. Maybe I'll solve a Putnam problem. So let's see some examples, right? And now I'll consider some nice polyhedra. So some nice polyhedra. And these nice polyhedra that I'm going to consider are the following. Let's say I'm going to consider tetrahedron, or I can consider the cube, right? These are very nice polyhedra. Well, I can also consider a soccer ball if you want, but that's still a nice polyhedra, but anyway. So let's see. For these, I would like to see, let's count the number of vertices, edges, and faces for these two polyhedra. So let's see, for the tetrahedron, so let's draw the following chart. Tetrahedron, and for cube. All right. So let's see, V, for V, E, and F. And then we want to see this formula. V minus E plus F. We want to see what it is. So let's see, how many vertices has a tetrahedron? Well, if you count them, it's 1, 2, 3, 4. How many edges? Well, if you look at them, edges has 1, 2, 3, 3, so there will be 6. How many faces? 1, 2, 3, 4, right? So 4 faces. So if you do 4, so it will be 4 minus 6 plus 4. Guess what? It will be 2. Let's look at the cube. How many vertices has a cube? So it has 1, 2, 3, 4, 1, 2, 3, 4, 8. Right? How many edges? So it has 1, 2, 3, 4, 4, 3, so it will be 12. How many faces? 6, right? Again, 8 minus 12 plus 6, it will give us 2. So as you can see, basically, if a polyhedron has, so let's say this. So basically, Euler's formula in this case says if a polyhedron has V vertices, E edges, and F faces, and then guess what? The same formula holds true. V minus E plus F will be 2, right? So as you have seen in these two examples, and in fact, like I said, even if I have a planar graph, right? More generally, if I have a planar graph that has V vertices, E edges, and divides the plane into F faces, including the outside one, right? Then the same formula holds true, right? And let me just give you examples of a planar graph. For example, this graph is planar, right? Like this. This is a planar graph, right? An example. Another one of planar graph is this one. Let's say this. And right, as you can see, these are planar graphs, right? But now let me give you an example of something that's not planar. And let me draw the following picture. Okay. All right. And this will be not, won't be planar. Let me. So this is not planar graph. All right. Well, I think this sums up basically most of the things that we need to know in graph theory. Like I said, there's so plenty of other things to know about, but I don't want to go into the whole theory, probably I'll lose it. So I'm just going to give you a quick example. I'm going to solve the following problem, which was not the hard one, it was an easy one. It was a Putnam B2 1997, I think. Yeah, probably. Anyway, and the problem says the following. So consider a polyhedron with at least 5 faces. It's important, 5 faces, such that exactly 3 edges emerge from each of its vertices. And now we're going to have the following. 2 players play the following game. All right, and the game is the following. Each player in turn signs his or her, well, these days is not even, you have to say they, but anyway, it's quite clear it was an all Putnam problem. His or her name on a previously unsigned face. Okay, the winner is the player okay, so the winner is the player who first succeeds right? Okay, so first succeeds in signing 3 faces that share a common vertex. Who first succeeds in signing 3 faces that share a common vertex. Okay. Now, okay, so this is the game. We would like to show that the player who signs first will always win. Will always win as well as possible. So that's the statement of the problem. And let's think of it, how we will use, let's look at the statement. Well, it's quite long, but anyway. The question is how we will like to, well, as you can see, if you look at the statement, it's quite clear. We're given a polyhedron with a number of faces, with a number of edges that emerge from each of its vertices. And we have this game played by these two players. And we would like to see how we can use Euler's formula. All right. So we have to show that that the player who signs first will always win, right? By playing as well as possible. Well, okay. All right, let's think. Well, if there is a face, let's say a face, let's call this F0, right? With 4 edges, right? With 4 edges with at least 4 adjacent faces. And let's call these, let's say, in this order, F1, F2, F3, F4, right? In this order. Then the first player, then let's say player number 1, right? Will assign F0, right? So now it's quite clear that regardless of where player number 2 signs, player number 1 will sign an adjacent face to F1, right? So let's write this, regardless of what player number 2 signs, right? Player number 1 signs a face which is adjacent to F0. To F0, right? And let's say F3. Okay. Because let's say face 1, F1 is probably signed by player 2. That's actually a very nice game. All right. Okay. Now, if player number 2 will sign F2, right? So let's see. If player number 2 signs F2, okay, then player 1 wins. Player number 1 wins by signing F4. All right. Otherwise, right? Otherwise, player number 1 signs f2 and wins, right? All right. Thus, well, as you can see now, it remains to show that the face f0 with 4 edges exists. So the only thing it remains for us is to show that that a face, let's say f0 with 4 edges exist. So that's the only thing we need to show. If we show this, then game over. So let's see. Now we would like to take into account Euler's formula. So by Euler's formula, we have the following. So we know that the number of, so f, in this case, f minus e plus v, right, will be 2 minus, and in this case, minus 2g. So it will be less than 2, right? Well, so it will be, all right. So since each vertex has 3 edges, right? And each edge shared by, so let's see. Since each edge is shared by 2 vertices, okay, we have that E will be nothing else than 3v over 2, right? And now, if all faces have just 3 edges, right? Okay. And each edge wait, 3 edges. All right, no. So if all faces have 3 edges, right? Let me think. Then by counting edges again, we will have the following. So we will have that, okay, I think at this point it becomes clear. We'll have that 3f is nothing else than just 2e. Or if you want to write this in the following way, 3f over 2 is e, which is nothing else than just 3v over 2. So the number of faces is the same as the number of vertices. And finally, this will give us, finally we have the formula here, right? This will give us that let's say v over 2, it will be nothing else than v minus 3v over 2, which is, wait. Okay, wait. Let me write it in this way. Plus v, right? Which will be, again, by Euler, f minus e plus v. And again, by using here Euler's formula. So by Euler's formula, this would be nothing else than, will be less or equal than 2. So v will be less than 4, and f will be greater or equal than 4, and we're done. All right, guys. So I think I'm gonna stop here. Thank you very much. I think this sums up the combinatorics. Anyway, I rushed through things with the graph theory. I didn't like to. I had to. There was a lot to cover. So anyway, and it's also very late. Okay, thank you. I'll see you next week.